Okay, today we're going to talk about motional EMF, and then that's going to lead to Faraday's law. I do this in reverse order than the book does, so I'm really going over 31.2 first because it's a little bit more intuitive, and then that leads to Faraday's law, which is a very general law. So I'm going to start off with a very specific, contrived situation, and then I'm just going to say, hey, this is true in general. Kind of like what we did for Gauss's law a long time ago. Now, EMF, you guys remember what EMF stands for? Yeah, and what, but it's not a force, is it? It is a voltage. So we're going to create it really should be called motional voltage. We're going to create a voltage by moving something. This is a big deal. I am going to create for you on paper the world's worst electric generator. Okay? We are going to generate electricity for the first time. Now, this is really going to be a bad electric generator, okay? But making it better is just engineering, you know. And as Sheldon once said, engineers are the Oompa Loompas of the scientific world. That's how snobby physicists think. Okay, I'm not a snobby physicist. I love engineers, but it is just engineering. Once you have the basic principles from physics, then it's just taking those principles and using them really, really effectively. So as an engineer, so what engineers do is they're going to take these results and they're going to make really efficient electric generators out of them. So we're going to generate electricity using a magnetic field. Now, here's the situation. I'm going to have, this is motional EMF here. I need a magnetic field. Now I'm just going to say, just for the sake of simplicity, it's a uniform field going into the paper here. Okay. And then I'm going to have a wire. And I could put a light bulb on that wire or whatever, but it's got some resistance. And then I'm going to put two conducting rails, and they could be like copper rods. You know, they're going down like this and going down like this. So we're kind of looking down on this experiment. And then I'm going to put a copper rod and I'm going to lay it on top of here. Hey, what's up? Yeah.
I thought I'd come by just to ask you a quick question.
Mm-hmm.
You sent me that thing about the link. Was the link not on there? Was it not working somewhere?
Oh, I just couldn't find it. Yeah.
Well, it's in the active department.
Oh, okay.
Maybe there's
I'll look for it.
Energy Academy. Let me know if there's someplace else where it isn't.
Okay.
If it's wrong somewhere, or there's someplace else. Okay, so.
Okay.
Because I thought I'd done it. That was what confused me.
Oh, all right. I haven't had a chance to check my email or any of that. So.
All right.
So thank you. Okay, so we're going to put this copper rod right on here. And then what we're going to do is we're going to slide it to the right. That just popped into my slide to the right. Crisscross. No, we're not going to crisscross. Okay, because that could cause a short. All right, now, so here's something very, very cool, you guys. And let's give this a length L across here. This is the length of the rod across the rails right here. Now, look what we got here. We've got everything here's a conductor. So we've got free moving charge particles, our pretend positive. Let's take a look at a pretend positive charge right here. Now remember that it's all electrically neutral, right? But there are free moving charge particles. Those valence electrons in a metal are not held by the atoms. They're just free to move around the metal, right? So they're free to move around. And now all of a sudden, I'm going to grab this thing and I'm going to pull it to the right. Well, look at what I've got here. I've got a charged particle that's moving in a magnetic field. Well, what does that charged particle feel? If you're moving in a magnetic field, it feels a force. So the charged particles in here that are moving, they're going to get pushed on, and we're going to create a current. Yeah, creating a current. If I move this thing to the right, I got F equals QV cross B. Okay, and now that's for each individual charge. But if I want to know, okay, how much, well, I've got, well, anyway, it's going to feel a force on it, and it's going to move up like that. And so my pretend positive charge is going to feel a force. Now, if your velocity is to the right and your magnetic field is down, you go V cross B, it's going to get pushed up. So there's the force acting on it. Now, so now I've got a force on this electric field, the force on this charged particle. Well, so here's the force on my charged particle. I'm going to divide that by the charge on my charged particle. And what is that called? Force per unit charge. This is cool, you guys. This is my magnetic force, isn't it? But it's the magnetic force it's going to push that charge up. But what is force per, if I take that force, that magnetic force, and divide it by the charge, what is force per charge? Huh? It's newtons per coulomb. And what is that? What kind of field? It's an electric field, baby. Yeah. So now we've got an electric field in here created by moving the charged particle through a magnetic field. So just like in the last thing we did, we're starting to see magnetism and electric fields and magnetic fields are really kind of merging. Yeah, is your head exploding yet? All right. So, well, what is this? This is QVB divided by Q. And so let's just deal with magnitudes here. So I have this electric field that's in here that's equal to the velocity V. Well, E is equal to V cross B, really. And this is a really profound idea, but for motional EMF, we're just going to get rid of the cross product and everything. We're just going to say the electric field is equal to V times B. But this electric field, through what distance is this electric field? Do we feel it? Well, it starts feeling it here, and it's going to go all the way through here. All of these are feeling. Here's the velocity field. So it's so my change in voltage across here is equal to E times L. Right? That's the voltage from here to here. Now, because the electric field is up, this is actually a voltage voltage drop, I believe. But yeah, let's just ignore that for right now. But this is equal to VB. the electric field is just the velocity that I move this guy times the strength of the magnetic field times L. Now, normally it's written like this: motional EMF. This is the voltage I get in this circuit. Now this is a circuit, right? It's a conducting path. If I expand this thing out like that, if I take this thing and I go whoosh, move it like that, I'm going to get a voltage that's equal to, and they just, for some reason, we write it VLV, which I don't really like, but all the books do it in that order, so I'm going to do it in that order. This is called motional EMF. In other words, this is a voltage you get just by moving this. Now, if you just have it sitting there and it's not moving, there's no voltage at all. But if I slide this thing to the right, I get a voltage, and that forces a current to flow. Okay, so this is motional EMF right here. Now, so now I got a voltage, but I also have a resistance, so I can figure out what my current is going to be. And if I move this at a constant velocity, we'll have a constant voltage, and therefore we'll have a constant current. And so we can figure out what that current is if you know the resistance. So V equals IR. So this is going to be BLV over R. That's the current that flows through here. And then all those things like power and all that apply, P equals I times V. And so you would multiply, you could just go on from there. And the book does. Read the book. It kind of goes into a little bit more detail here. But this is the big deal right here, BLV. You get, now, by the way, if I've got a current flowing through here, because I'm moving this thing to the right, well, what's true about a current, and that means you have to have, if I'm increasing the voltage from here to here, that means I have to have a voltage drop from here to here, and that means energy is exiting the circuit through that resistor. Well, if energy exits the circuit, that means energy has to be put into the circuit. Where's that energy coming from? I know, you guys are fuzzy. Well, you're not fuzzy. Your brain is getting. Look, I got a current right there, right? Okay, right? This magnetic force right here is forcing charges to move upwards. So that gives me a current, right? Well, now I've got a current in a magnetic field. And what is that? If I have a current, F equals I L cross B. Well, if I go L, here's the direction of the current. Let me zoom out even more. I got a current moving up here, IL cross B. That means there's a force like this. There's a magnetic force on this wire moving to the left. Well, but I said this velocity is constant, right? So what do you have to do? You have to cancel out this force. That means somebody from the outside world has to pull on it. So if you physically grab this thing and start moving it, you're going to feel a resistive force, that magnetic force pulling the opposite direction, which means that you got to overcome that force. So I'm going to apply a force to the right through a distance. Well, if I apply a force to the right through a distance, I'm doing work. That energy that's lighting this light bulb is coming from me pulling on this thing. I'm doing work, and that work is being transferred into the electricity that comes out here. I've created a power plant. the world's worst power plant, but I got to go to do that, all right? Because I've got a current here, and that current creates a force. Well, I have to apply an opposing force, which means I have to do work. And that work comes out of the circuit through the resistor, as like a light bulb or something like that. Okay? So, now, here's what I want you to see also. What is velocity? Velocity is equal to dx dt, right? Let's call this the x-axis along that rail right there. There's my x-axis. Oh, oops. Well, this has a little like that, see? These are crosses, these are x's. That's an x, I mean. It's only one of them. There's an excess of x's. All right. So, now, where am I going with this? Well, let's take a look at this. Let's take a look at it at this instant in time where this rail is right here. So I'm going to say this is my origin. So this is at some position x. Okay, there, sorry, another x. Now we do have x's. Notice that we have an area here, don't we? And we have a magnetic field through that area. Well, what is that area? The area here is x times L. But this is moving at a certain velocity. Oh, and then I'm going to take this and I'm going to multiply it by, I'm just going to show you something here. I'm just going to multiply it by the magnetic field, the amount of, by the magnetic field in here. Is that, wait a minute, I'm messing this up. Oh, that's right. Sorry, starting over. Now, here's what okay. How much magnetic flux is contained by the, remember we're talking about like with Ampere's law, how much magnetic flux is contained by this loop here? Well, the amount of magnetic flux is equal to B dot A. Okay, the strength of the magnetic field times the area is equal to the total amount of flux. Well, this area is just x times L. Well, now what I'm going to do is I'm going to take the derivative of both sides. And I'm going to, and when this happens, I'm going to derive Faraday's law. So the rate at which the magnetic flux is increasing in this circuit, right? If I pull this to the right, I'm increasing the amount of magnetic flux in there. Well, B is a constant, right? We said let B be uniform. L is a constant. So X is the only thing that's changing with time. So this is going to be B times L times dx dt. Well, what is B times L times dx dt? What is dx dt? It's the velocity that I'm pulling this thing to the right. And so this is BLV. But what is that? What is BLV? That's the change in voltage, delta V, sorry. So this is the voltage I get, that I got up here. Now I'm going to call that voltage, I'm just going to call it E for EMF. And now, so here I've got this guy is equal to the rate at which magnetic flux is changing in the circuit. And here's where I'm going to do the thing I said I was going to do, where I just say, okay, in this very contrived situation, it can be shown that in general this is true. The voltage I get, and this is true for all electric generators, is going to be equal to the rate at which I change magnetic flux. So I showed it for this, but for any loop of wire, any circuit you have, if you change the amount of magnetic flux penetrating through that loop, you're going to get a voltage. Now I'm going to do something, and I know that these are a lot of concepts to get, and you're going to need to think and study a lot. I don't know if you want to watch this video again. I might redo this because it's been there was a lack of caffeine was involved. But I'm going to put a negative here, and we're going to get to that negative later on. But here's what it says, is that if you change the amount of magnetic flux penetrating through a loop of wire, that you will get a voltage in that wire. And this is how electric generators work. If you have an electric generator, what they do is they have loops, they have multiple loops. They have loops and loops and loops and loops of wire, and they spin it in a magnetic field. And when they spin it in a magnetic field, they're constantly changing the amount of magnetic flux through that loop, and that creates a current, or a voltage in that loop, which creates a current, and we're generating electricity. Now it takes work to do that. You have to put energy in to it to make it do that, but this is the theoretical basis anyway of electric generators. And this right here is called Faraday's law. One last thing. Why is this negative here? Well, and this is going to get us to Lenz's law, which is coming up. Let's take a look at, let me redraw it. This will be the last thing, because I've talked too long already. Here's my motional EMF diagram again. So here's the magnetic field. Here's here are my two rail. Oh, and here's my rail on here. And I'm going to pull this thing with the velocity to the right. Now we said, hey, QV cross B, that's going to create a current like this. And that current is going to circulate like this. And we just said that, hey, that voltage that I get in this circuit is equal to the rate at which I change the magnetic flux contained by this loop. But why do we put the negative here? No, now, hey, what do you notice about the amount? We're increasing the amount of magnetic flux through this loop, right? So in another minute, or a few moments, this thing's going to be over here, and now I've got 4 crosses in there instead of just 2. So we're increasing the amount of magnetic flux. But look at what this current is trying to do. The current's flowing this way, right? In a circle. What does current create? Current creates its own magnetic field. So we've got 2 magnetic fields here now. We got this magnetic field that I was given, but now I'm going to create, I've got a magnetic field that's being created by the current in the circuit. Now, if I grab, I can use the solenoid or the loop rule, or I can just grab the wire. Let's just grab the wire. I like that one the best. So here I've got a current like this that's being, if I pull this to the right, I've got a current like that. Now grab the wire and tell me the direction of the flux. If I grab it, do you see that this current creates a flux that is out of the paper here, right? It's coming up, and that's what this negative sign means. And this is one of the most complicated and most difficult concepts of the whole year. And this is getting to Lenz's law, and we're going to cover it again. If I'm increasing the magnetic flux in my loop, that will generate a voltage. And that voltage will generate a current. But that current creates its own magnetic field, and that magnetic field will oppose the rate of change of magnetic flux through it. It's going to try, it says, no, I do not like change. You are trying to increase the amount of magnetic flux through my loop, and I don't like it. So I'm going to create a current that's going to oppose it. So I'm trying to get more and more and more flux into the paper here as I pull it to the right. That generates a current that circulates counterclockwise here. Well, a counterclockwise current creates magnetic flux up. It opposes the increasing magnetic flux down. Now, what if I moved it the other way? So here's my rail right here. What if I force it to move the other way? Well, that's going to, if I'm a little positive charge and I go QV cross B, right? This little guy's going to get pushed downwards now, which means I've now got a current flowing down, which means now the current is circulating clockwise. Now what we're doing is we're reducing the amount of magnetic flux through this, right? We're reducing the amount of magnetic flux that's downward into the paper, and it says, no, I'll keep it the way it is. Because look, grab the wire now. It tries to create magnetic flux that's going into the board. So it creates a current that creates a magnetic field that opposes the rate of change of magnetic flux through the loop. Now, if your brain isn't completely jelly by now, then you're amazing, okay? Because this is, I don't blame you. This is going to take a lot of time of thinking. Now, I just want to say, when I was in college and I learned this thing the first time, I gave up on it. I said, I'll never get it. I'm just no good at E&M. I'm genetically deficient. Okay. Now then I got a job where I had to teach this stuff. Okay, so then I had to really learn it. What? And hey, let me tell you, a paycheck is a great motivator. Yeah, I will pay you. Yes, I will pay you. If you learn this stuff, I'll bring in some donuts or something for you.
They should have a policy where, like, if you get a 5 on the AP test, like, the teachers will pay you back for the AP. Not the teachers, but, like, the school should pay you back for the AP test.
Oh, that would be a good rule.
That would really, like, motivate.
That's a good idea. All right, well, that's enough for now.